Hi, this is Mr. Manley. In this video, we're going to look at several problems where we're solving trigonometric equations. I'm going to start with the basic and get to some more complex examples. What I really want you to pay attention to here is just the properties of equality, the algebra of the problem, and then the trigonometry really just comes in at the end. So with this problem here, whenever I see a variable, or not a variable, whenever I see a denominator, I'm actually going to multiply through by that denominator so that I don't have to deal with it. So with this, I'm going to multiply through by 4. That's going to be 16 minus 2 cosine theta equals 16 plus rad 2. And then I can see here that I have a 16 on the left and a 16 on the right. Cosine theta is equal to negative rad 2 over 2. Okay, so now I'm thinking about what angle has a cosine value of negative rad 2 over 2. You should be able to do this without a calculator. Should be able to do this with a unit circle. For me, since the cosine of theta is equal to x over r, and I'm looking at a unit circle with a radius of 1, so that means that this radius here is 1. Then I'm looking for an x coordinate of rad 2 over 2, or actually negative rad 2 over 2. And I'm seeing that that's going to happen here at negative rad 2 over 2, rad 2 over 2, which is an angle of 3 pi over 4. And it's happening here, right? At negative rad 2 over 2, negative rad 2 over 2, which is 5 pi over 4. So I'm not going into too much detail about how to find those. You need to go back and review your unit circle if you're not seeing how I'm getting to those so quickly. With that said, I now know that theta is equal to 3 pi over 4. And since there's no interval on this, I'm going to say plus 2 pi n. And then likewise with the 5 pi over 4, I'm going to say plus 2 pi n. And that's indicating that the answers are these angles, and then any coterminal angle, any angle that is coterminal with those. So that's the solution there. Okay, with this problem, we're noticing that we've got a mismatch, right? I've got cosine and some sines. And in order to solve, and unless I see a way that I'm going to be able to factor, I'm going to have to make some adjustment here. First of all, I mean, what I want to do is when I'm solving, I typically want to set this equal to 0, right? That is almost synonymous with solving. I mean, there are scenarios in which we wouldn't need to set it equal to 0, but you would recognize that scenario. Like if I had sine squared theta, let's go 2 equals 1, and then maybe a 2 here, plus 2, something like that. So there, I don't need to set this equal to 0. I suppose I could, but I see that I'm going to be able to isolate down to a perfect square. So understand what I mean by that. If I've got a perfect square, I don't need to set it equal to 0. I can isolate the perfect square and then take the square root of both sides. Okay, but that should be obvious if you see that case developing, which is in this case. In this case, I've got this mismatch here. So what I'm going to lean on, or what I'm going to notice here, and very often when I'm working trigonometrically, is that I can do a substitution to make the equation, in this case, to make it solvable. Something that we'll say in calculus is we want to make it more friendly to operate on in the way that we want to. But in this case, it's simply I need to do some adjustment here to make it solvable. So what I'm noticing is that I've got the signs here. If I could rewrite the cosine in terms of sine, then I would have this in a better position. So looking at the Pythagorean identity here, I can see that if I solve it for cosine squared, I will have 1 minus sine squared theta. Now you see that? The cosine squared is equal to this 1 minus sine squared. So I can make that substitution. I'm going to make that substitution. 1 minus sine squared theta. That is cosine squared theta. And then the rest of the expression is there. All right, and let's combine our terms. I've got -2 sine squared theta minus sine theta plus 1. I don't like to have a leading coefficient that is negative, so I'm going to multiply through by a -1 and just flip all these signs. SIGN sign. And now I see I have a quadratic, right? I've got this quadratic, squared, first power, constant. And for that, I am going to set up a FOIL. See where this is going? That I've got 2 sine theta times sine theta is 2 sine squared theta. And then I've got this -1 here. So I'm going to have a 1 and a -1. And I want the +1 to give me the +2. And then the -1 to give me the -1. And that'll give me a sine theta. So that's factored. And then I can use the zero product property, right? And say that sine theta is equal to 1/2. Sine theta is equal to -1. Again, no domain limitation on this, so I'm going to use plus 2 pi n. Where is sine theta, or where's theta? Yeah, sine theta. Where's sine theta equal to 1/2? So that's a y coordinate of 1/2. That's happening at pi over 6. I'll put it in set notation here. Plus 2 pi n. That's happening at 5 pi over 6 plus 2 pi n. And then when is sine theta equal to -1 for what angle? I'll tell you the way I do that, I actually don't think about the unit circle. I go to the graph. I go, oh, it's equal to -1 down here at that minimum value. And where's that at? I know that's at 3 pi over 2. You can use the unit circle, but I always think about the graph when I'm talking about that. So 3 pi over 2 plus 2 pi n. And there are all my solutions. Right there. Okay, another case here is we have a multiple angle. So that's when I have a coefficient on theta, I would say. But, probably a 2, 3, or 4 is what I'm talking about. All right, here I'm going to combine like terms. I've got this -3 cosecant of 2 theta plus pi over 3, and I've got a 2 theta plus pi over 3 over here. So those are like terms I can combine. We got minus 3 of them over here and minus 2 of them over here. So I'm going to bring these over by adding 3 cosecant to both sides. And then I'm going to move this 3 over to this side, right? So on the left, I'm going to have 1 minus 3 is negative 2. And on the right, I'm going to have, that's 3 minus 2 is 1 cosecant 2 theta plus pi over 3. And as I've said many times, if you're taking pre-calculus with me, I've said, look, if this were an angle, theta, then I would be saying, what angle has a cosecant value of negative 2? And something that I see students do that I actually don't hate is that, well, I could just flip this and say cosecant is the reciprocal of sine. So I could go like this if we're more comfortable with sine. See that? Now, is that too big of a jump for you? I mean, to get from here to here, I'm going negative 2 is equal to 1 over sine of that argument, 2 theta plus pi over 3. And then I'm just reciprocating both sides, right? And then from there, we're on to the unit circle. So I'm looking for the y coordinate of negative 1/2. So that's happening here and here at rad 3 over 2 negative 1/2, which is 11 pi over 6, and at negative rad 3 over 2 negative 1/2, which is at 7 pi over 6. Right, so those are the angles that will get me the negative 1/2. So from there, I'm going to have 2 statements, right? 2 theta plus pi over 3 is equal to 7 pi over 6, and there's the plus 2 pi n. And then if I solve for theta, I get 2 theta is equal to 7 pi over 6 minus pi over 3 is 5 pi over 6. You can work that out if you need to. Plus 2 pi n, and then divide by the 2 or multiply by 1/2, however you want to think of that. I get 5 pi over 12 plus pi n when I divide by 2. All right, and then similarly, I would have the 2 theta plus pi over 3 equal to 11 pi over 6 plus 2 pi n. And then 2 theta is equal to 9 pi over 6 plus 2 pi n divided by 2. And I get 9 pi over 12 plus pi n. And, we can put that all together up here. Let's say my solution set is 5 pi over 12 plus pi n. And then the 9 pi over 12, that's 3 pi over 4, right? 3 pi over 4 plus pi n. And there. So that's that. And then what if I take one of these? I'm going to do a multiple angle that has a domain restriction. So let's take a look at one of those. Again, I've got a denominator here, that 4. So I'm going to multiply through by 4. 16 plus, and that'll be 10 cosine 3 theta plus pi over 4 equals 16 plus rad 2. What did I multiply by? I multiplied by 4. 4, 4, so I got 12 of these cosine 3 theta plus pi over 4s. All right, I've got, so I got 12 of these over here and 10 of them over here. Let's move them to the right. And let's notice that we have the 16, right? So the 16 cancels out. And I'm also going to move this over to the left side. So what happens there? I get negative rad 2 equal to 2 cosine of 3 theta plus pi over 4. Right, then I'll divide by the 2, right? So negative rad 2 over 2 equals cosine of 3 theta plus pi over 4. So 3 theta plus pi over 4 is equal to, all right, so what angle has a cosine value of negative rad 2 over 2? Didn't we see that back here? Was that? Yeah, that was all the way back here. You see? We were doing that back here, negative rad 2 over 2. So it's 3 pi over 4 and 5 pi over 4. That was this one and this one. So let's do that. 3 pi over 4 and 5 pi over 4. So that's equal to, 3 pi over 4 plus 2 pi n. And let's just put the 5 pi over 4 right there as well, plus 2 pi n. And then there's an easy subtraction, right? 3 pi over 4 minus pi over 4 is 2 pi over 4, which we'll call pi over 2, right? 2 pi over 4 is pi over 2. So that's 3 theta equals pi over 2 plus the 2 pi n. And then 5 pi over 4 minus pi over 4 is 4 pi over 4, which is just a pi plus 2 pi n. All right, and then divide through by 3. Get theta equals pi over 6 plus 2 pi over 3n. And then I get pi over 3 plus 2 pi over 3n. But in this case, I only want the solutions that are between 0 and 2 pi. Right now, this n is giving me infinite solutions. So what do? I'm going to let n equals 0 here. So I'm going to let n equal 0 there, and that'll give me pi over 6. And then I'm going to let n equal 1, and that'll give me 5 pi over 6. And then I'm just going to keep adding 4 pi over 6 from there. So that'll be 9 pi over 6. And then, okay, now if I try to add the next one, it's going to be 13 pi over 6. And that is going to be that's more than 2 pi. So this here, that's more than 2 pi. So I don't want that. All right, if you're having trouble with my values here, well, that's the nice thing about a video. You can stop and you can work it out yourself. But all I'm doing here is I'm adding, to get to this, I'm adding 2 pi over 3 here, and then I'm adding 2 pi over 3 again there. All right. And maybe I want to simplify this. What is that? 3 pi over 2. Yep, 9 pi over 6 is 3 pi over 2, right? We'll go ahead and simplify that. Okay, and then moving on to this one over here, the pi over 3. This should be pretty simple. Pi over 3, if I let n be 0, I'm going to have pi over 3. If I add 2 pi over 3, I'm going to have 3 pi over 3, which is pi, and then add 3 again, and I'm going to have, add 2 pi over 3 again, and what am I going to have, 5 pi over 3? 5 pi over 3. Is that right? 3, 4, 5, yeah. Yeah, and if I add it again, I'd be more than 2 pi, so I'm going to stop there. All right, so there's my solutions. sometimes I'm writing the solutions in like this set notation, and sometimes I'm just saying, I guess I did set notation there, there. All right, so here I just said theta equals. There's no rhyme or reason to that. That's just what is convenient in the moment. All right, so there's a variety of equations, and I know like I mean, I guess maybe the challenging part, I don't know if it's the unit circle or just the trigonometry in general that are at the end, the inverse trigonometry. But you want to really focus on not making these errors up here, right? I mean, this is just properties of equality to advance this to this point here. And that's where I see a lot of errors sometimes. Okay. So that'll be it. That's kind of just scratching the surface. There's other equations to look at as far as solving goes, but that's a good start.